sloppy town over here. Let's try again. Wait, which one are you seeing? You're seeing this one, right? You see the PowerPoint?
Yep, we do.
Okay. I don't know why I call it PowerPoint. It's a keynote. Can't disrespect. Hi, everybody. Welcome back to Python for STEM. So we are still here. I know that perhaps some of you were a little confused because we had a little calendar hiccup where we weren't announced, but here we are, and we're still going to be here for at least a couple more weeks, maybe more. We'll keep you updated as we go along. So why don't we jump in? So as promised, today we're going to talk about fitting, which is a wonderful way for you to be able to start analyzing your own data. To motivate this, we're going to give you some data that we've generated for you to analyze, and we have some exercises, and we decided to use some sort of distributions which are not Gaussian, but rather they follow a distribution that is referred to as a Breit-Wigner distribution. So we'll introduce what that means. First, as always, we'll start with administrative details because those are the funnest, right? And so administrative questions, issues that you may have, probably most of them can be answered by you just sending us an email to pythonforphysics@odu.edu. That will automatically give you all the links that you want and more. And so just go there and you'll get links for everything. And as always, I like to start by asking you, how you doing? And how are you in your part of the world? Are you enjoying yourself? Are you enjoying coding more? Like, I mean, I know that some of you have some coding experience, but for those of you that are coding for the first time, are you enjoying it more than you expected? Hopefully so. Hopefully you're not enjoying it less than you expected. That would make me sad. You're welcome to make me sad, but literally tell us in the Q&A box, how you doing? So we like to hear, you know, we know that it's not the same as being in person, but, you know, hearing from you really makes us happy. And so tell us about how you're doing. All right. I see that somebody put something in the chat. Anybody want to read?
Abby says they're doing great.
Oh, that's awesome, Abby. I'm glad to hear it. It's also okay if you're not feeling great. You could tell us like, today's not that great to say. And then hopefully we'll like try to make it better, right? We don't always have to have a great day, right? But I'm glad that Abby's having a great day. Okay, so why don't we start with a mini review, just to recap what our exercises were in the last class. Let me jump ahead. We created an exercise where we encourage you to evaluate pi, so 3.414, blah, 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 using random numbers, right? And we created this little like sand pit where you throw random numbers, and if they fall inside of the circle, so it's a 2x2 square, right? And there's a circle with a radius of 1. And so if they fall within the circle, then they become blue. If they fall inside, they're red. And then the ratio between the blue and the total number of points is going to be related to pi. We derived that. And so you should have seen that as a function of the number of points, you start converging to some number that is very, very close to pi. Okay. And so we also challenge you to calculate the error associated with that and a distribution for some large number. And so are people able to, have people been able to calculate plots like this or like this at least? Have people been close to calculating pi to some level of precision using random numbers? Are there challenges out there that people want to talk about? Perhaps not everybody has gotten there. That's okay. If you have and you have any questions, feel free to ask them in case they might be of use to others. And let me foreshadow a question of yours. Some of you will probably ask about the mentor program. We're like just like an inch away from sending emails. And so if you sign up to be part of the mentor program, and you're interested in working with me and or Andrew Jakura, Andrew and I, Dr. Jakura, I should say, but Andrew and I will be co-hosting the mentor program for nuclear physics and programming. And so we'll be working together on that. And we're going to be sending an email to everybody that applied. And essentially everybody that applied will be able to work with us. So that's going to require some creativity on our side. This is a very ambitious thing that we're doing, so you'll have to be patient. If you didn't apply to work with us, but you're still interested, you can shoot us a message and we can add you to the list. Okay. All right, so that's that. And then the second problem that we gave you was one associated with the decay of a particle, which originally was at rest, and at some later time it decayed to two particles. We gave you the mass of particle A, we gave you the mass of particle B, we gave you the momentum of particle B, and then we use our favorite quantities that obey conservation, namely energy and momentum, to then that tell us a constraint on the mass of particle C, even though what we can see is particle A, particle B we can see, but we can see particle B, but we can't see particle C, right? And this is a very realistic scenario. This happens many times. An easy example where you can have a particle with a charge that decays to two particles, one which is charged, the other one is neutral, and then your detectors may just not be able to see that neutral particle. Some neutral particles we can in fact see, but not all. So neutrinos is the example of the particle that is very hard to detect, right? And so that was the example that I considered. But other neutral particles we can detect very well these days. Okay, so then we use some.
Raul.
Yep.
Can I stop you for a moment? Just before we get too far away from the Pi project?
Yeah.
We had a slight question on the Slack that the students have been talking to each other about, but it was about runtime. And it's been a minute since I've run this. Does this take a while, or should they expect quicker times, slower times?
It depends. I can't remember. I haven't run this in a while, but this could take certainly. I mean, if you're doing something that is 100 points, it should be seconds at most, right? And so it should be fairly fast here. The place where you might be able to, so Python is notoriously small for doing for loops. So if you're doing for loops, perhaps, especially if they're nested, if you're doing like double for loops, that could slow down your code quite a bit. I do everything using arrays and built-in functions like sums and things like that. And I have some tricks for speeding it up. So I don't remember. If you're doing things in the order of like 100 points, it should be fairly fast, sorry. If you're doing things in the order of 1 million, then it could take maybe half a minute or something like that. I can't remember exactly the speeds, but it shouldn't take minutes. So if it's taking minutes, you're probably using some sort of function that is slow for Python, or you're building too many redundancies, right? You should be able to speed it up by cleaning up your code. If that's the case, what I would suggest to everybody, this is the thing that I would always suggest, is that is keep your version that is slow. And so you have a script that is called it slow, pi_slow, right? It works, but it's slow, right? Now try to grab that code, right? Copy it over, right? So keep the old copy and make a new one. And then try to play around with things where you're trying to remove for loops, for example, and use arrays, things like that to speed it up. And then test that the results agree, right? Your previous slow code and your new one, right? And then that's going to be a way for you to start doing benchmarks in time, so that you're pushing your speeds while still having something that that honest to God works, right? So that's my advice. Maybe Connor has something to say.
No, that sounds like pretty good advice for the most part. Yeah, definitely look into NumPy's built-in functions or anything. Yeah, I think Raul hit it on the head there. So I think somebody else was asking about any updates on marble guessing. I think that we have like 13 guesses right now, and it's a little bit hard to get a nice bell curve from that. So, I mean, if you could get your friends or family to give guesses, that would be great. You can put multiple in the chat. I think we can figure that out. Yeah, we really need more data for that to show what we wanted to show.
I mean, that's brilliant. Connor, did you ask your family?
I did. I got 2 extra guesses from my friends, but yeah, I think my little brother knows exactly how many marbles there are. So
that's okay. He won't skew it, right? Okay. I mean, it's just one data point, right? What about, did you ask the people in our research group at ODU?
Oh, that's a good, yeah. I think Felipe gave a guess, but yeah, I should put a
yeah, just put it on the Skype chat
there. Yeah.
Cool.
Okay. And another anonymous attendee is asking, are while loops faster then? I don't think so. No, it's just because Python is interpreted rather than compiled. So there's another program in between, your Python code and the computer that looks at the text that you've written and is like, okay, well, I see the word well, that means I need to go and, do some stuff. And that process is quite slow compared to, compiled program. And yeah, it's just generally looping or doing anything in Python is not super fast, but it's a convenient language to use.
Yeah, I mean, if you use anything like vector matrix manipulations is very fast. So that's just my recommendation is that a lot of times you think, I mean, the way that we're typically taught is to treat object, to do iterations using for loops. And for a lot of times that, there's no way around it, but most of the times you can get around it and write things in an array format. So I would strongly recommend you just rethinking about that. So, all right. I don't see any more questions. So should we proceed?
I think so.
All right, good. So then I gave you some data for the 2-particle decay for the momenta of the detected B particle, right? We know the mass of A, mass of B. I gave you the momentum for B. And then assuming that we have some detector that can't tell you exactly the value of the momentum, the question was grab the noisy data, right? Make a histogram of the noisy momentum, and then try to predict the mass of particle C. So the question is, did you get to do it? Did everybody do it? Do people have predictions? Anybody predict it? Yeah, guys. What were you doing? Enjoying your summer this weekend? All right, maybe I'll skip the next one. All right, I skipped it. So you won't see the result. I'll let you keep trying. I'll wait for your guesses. All right. Are there any questions that are remaining before we start touching on a new subject? Or any questions about the tasks that you still have to do? No. All right. Why don't we just go ahead? Let's just keep going. Okay. So like I said, today we're going to do basically more data analysis, and we're going to do a little bit more particle physics because it's fun. But the ideas are going to be universal. They're not just relevant for particle physics. But I figured I would talk a little bit about particle physics because I love it. And so I'm going to tell you about essentially how do we discover particles? How do we know that when we see, we see these kinds of behavior in scattering experiments? What do those scattering experiments mean? And how do we deduce the presence of some particle in there? And I figured I would give you the example of the Higgs, which led to a Nobel Prize a couple, maybe now a decade ago, which was discovered at LHC. I've already mentioned this before. The Nobel Prize figure, there was two figures actually, but one of the figures looks just like this. It's just this tiny little bump. In fact, it's this bump here where what is being detected is the number of decays of a Higgs going to 2 photons. So it's 2 photons and that have the same property, that are constructed in such a way that they have the same properties as the Higgs. And what you're seeing is a tiny little enhancement here, which is being subtracted. This curve is being subtracted. And so then now you see this enhancement a little bit clearer. So how do we know that this enhancement led people to believe that there had to be a particle there? Is something that I will touch on. But before that, I figured I would start with, why do we care about the Higgs in the first place? Well, so the Higgs is named after Peter Higgs, and it was also predicted by other folks, including Francois Englert. And the Higgs is quoted to be the particle that is responsible for giving the mass to other particles in the Standard Model. Okay, and so these are the particles that we know that exist in the Standard Model. Just to remind you, a Standard Model it's just basically the foundational rules that we found in the universe at the subatomic level. It just describes the three of the 4 fundamental forces, namely electricity and magnetism, the weak nuclear force, and the strong nuclear force, which I've touched on before. And there's 17 particles inside of the Standard Model, and the Higgs is the one that is responsible for giving masses to the quarks, which are up here, the up charm top, down strange bottom, but it's also responsible for giving masses to the leptons here, namely the electron, muon, and tau. The neutrinos have a mass, but we don't know where it comes from, in fact. And the Higgs also gives masses to the W and the Z, and also gives masses to itself. And so I figured I would point you to this talk, which I've already pointed you to before, but let me just put it on the chat in case you haven't seen it or you missed my pitch for it. But we had a really beautiful talk last year by one of my close collaborators, Max Hansen, who was at the time a staff member at CERN. He gave us an overview of the history of CERN. And so if you haven't seen it, I encourage you to go check it out. He just gave a really nice story of the particles discoveries and those that were discovered at CERN, and what's how we learn from CERN and what will we learn from it in the future. There's also a nice video that explains why the Higgs matters, which I like to point students to, but it's a little too long for me to show it, so I won't go there. But I encourage you to go to YouTube and look for the Higgs explained. And so here's my little explanation of what the Higgs is, and also why what we can maybe deduce from it, and what is correct about it and what isn't. So it turns out that the Higgs gives mass to the quarks. That's absolutely true. Okay, we know that the proton and the neutron, what we are made out of, is made out of quarks and gluons, right? And we also know that most of our mass is stored in our nuclei. So most of our mass is just due to the mass of the proton and the neutron. These are, of course, the building blocks of things like hydrogen, but also all the different atoms and molecules out there in nature, right? And so there's a bit of a simplistic conclusion that we can make, right? Since the Higgs gives masses to the quarks, the gluons don't have a mass, right? And our mass is stored in protons and neutrons, which are the things that gives masses to atoms, molecules of all kinds, and including everything that we're made out of, right? Then we would naively conclude, then the Higgs, namely the Higgs particle, should be the source of our mass. This is perfectly reasonable, but it turns out that it's just not true at all. And the reason why is because the gluons, the interactions of the gluons with the quarks, but also with themselves, is so highly energetic that the energy stored in this gluonic excitations inside of the proton are in fact most of the source of our masses. So our mass, most of it is not coming from the Higgs, but it's coming from the stored energy inside the gluon particles, the gluonic particles. And so we'll come back to this in a little bit. Well, how do we know this, and how we can see that now from our simulations? So you're going to play with this, the data from these simulations. But first, I'm going to jump into, so this tells you that the Higgs is important. It's important because it brings the standard model together. It gives the masses to the quarks and leptons, but it's in fact not the main source of our mass. Okay, so it's very important, but it's not the source of all our mass. Okay, so it's the source of masses of the mass of subatomic particles, but not everything. And so we'll come back to this later. But first, let's talk about how do we even know that these little bumps that we see in experiments are particles, and we're going to see how we can deduce the masses from them. And so for that, I figured I would give you a brief overview of how particle detectors work, and why do we use them and why they're so important. And the first thing that we need to do, in my little sketch of particle detectors is we need to, so I figured for the first thing we should imagine doing, right, is that we need to have some theoretical motivation of why we need to build detectors, that we need to make some sort of prediction of what we will see, which motivates the community to come together and build an accelerator. This is relatively easy to say, it's very hard to do. And this is, in general, we have a shortage of particle accelerators because it's very hard to make these kinds of motivations, and it's hard to bring the field together, but it's a necessary first step. And what we actually can predict from quantum mechanics, meaning the rules that govern the subatomic world, are probabilities of events. We can only predict the probability that something will happen. Quantum mechanics in the subatomic world is not deterministic, right? In classical mechanics, everything is deterministic. So if I grab some object, what can I grab? I'm not going to throw anything here, but if I had a ball and I knew at what speed it was going, when, and in which direction it was going, then I could predict how far it will go, even if I take into account air resistance, right? I can predict how far it will go, where it will land, etc. Right? I have a complete prediction of everything. In quantum mechanics, you don't. You can't simultaneously know the position exactly of a particle and its direction, and so we lose sight of any notion of complete predictability. What we do have is predictability on the probabilities of things happening. And so that's what we do when we're making predictions. We're predicting the probability that certain events will take place. And if this is challenging, right, conceptually, that the nature is not predictable, right? This was challenging to a lot of people in the community, including famously Albert Einstein and many others. Although Albert Einstein had very sophisticated arguments and that pushed the envelopes and the notions of quantum mechanics. So, it's not that Albert wasn't the sharpest tool in the shed. He was, in fact, remarkably brilliant. But it was something that was it went against the grain of many folks. Now, these days, we take it for granted. And so once we have a particle accelerator, the job of particle accelerators is to accelerate particles, and we accelerate particles close to the speed of light. The idea for doing this is that eventually what we're going to do is smash them against each other with sufficient amount of energy that new things could happen, new phenomena could come out of this. And in fact, what ends up happening is that if in quantum mechanics, if you have two particles that can in general either annihilate each other completely and then create other particles, because energy has to be conserved, right? We already touched on this. Energy always has to be conserved. Momentum always has to be conserved, right? And so if you have two particles being annihilated, right, that energy has to appear some other way. And so it can appear as other particles. And so this can happen. And instead of showing this like little, I don't know, more classical kind of picture of collisions, right, of objects, like namely cars, we can have a little more realistic cartoon of what can happen is if I accelerate two protons, for example, which is what happens at the Large Hadron Collider. What can happen is that at some original time, they're far away from each other. And then once they get closer, they can exchange all sorts of effects. And then there's some intermediate interaction region, and then they go off in their merry way, and you can detect them. You can create new particles. Many, many things can happen. And here's a simulation of a reaction that took place at RIC, which is in Brookhaven National Lab in New York, in the state of New York, where you're seeing each one of these little tracks corresponds to a subatomic particle that is being detected, right? And so step number 2, smash. Step number 3, detect this debris of particles and isolate all the particles as well as their energy, momentum, where they're going. And then once you've been able to do all this, you can effectively reconstruct the original instant of the reaction and be able to deduce what happened. How did the particles in fact interact with each other? Of course, we have a particle accelerator here at Jefferson Lab. We've told you about this many times, and we have a JLab tour that you can check out. So go ahead and do that. And here, I'll put on the chat, and then we'll get back to just for your convenience. So I'll put it right there. And so instead of me telling you more about Jefferson Lab, you can just go check out the tour. And so how do these, if I zoom out, what's happening? So imagine that I have two particles, okay? And here I've constructed a cartoon of a detector. In that tour at Jefferson Lab, you can see really, you can actually look at the detector. It's remarkably fancy, but as a theorist, I can simplify things. And so what can happen is that most of the times the particles, when they're zipping through each other, they're just going to pass each other, and then they might be deflected because let's say they have opposite charges, and so they repel from each other. And then what happens is that once they hit one of these buckets, there's a count. That count gets translated into a current, and that current goes into a computer, right? And you see that there was an event in that instant. Most of the times, the particles just don't interact, and so they just pass each other. But what you end up seeing is that, many times you see events, and you see some sort of distribution, right? You start collecting data in different points, right? And what you're doing is counting the number of events. And that's the first approximation. What you're seeing here is just a counting of events, okay? This has been subtracted over some overall number, but essentially that's what's happening. And I'll come back to a second, and why there could be a bump, right? Eventually, what you want to do is compare the number of events that you see from experiment, compare that with what you would see, what you predicted from theory. And this is remarkably important because without the theory, we can't make sense of experiments, but without the experiments, we can't know which theory is right? So theory and experiments both have to be there for us to be able to make sense of nature. And ultimately, what we want to do is, once we predicted which theory is right, is to be able to reconstruct the initial events, the initial conditions on how the particles interacted. We don't see that with our eyes. We can't see this with detectors. So we need the theory to essentially rewind the movie to the instant where the particles interacted. So that is just crucial. Okay, so that's that. Now that we've essentially constructed and motivated our particle accelerator following these steps, right? Let me jump ahead and start talking about resonant phenomena, okay? So it turns out that particles, strings, and bridges, and many other things have a very common kind of underlying description, which is they possess some similarities. And in fact, they can all be understood as resonating systems. Whether it's a string, right? If you have a string and you plug on it, right, it's going to resonate at some particular frequency. If you have a bridge that has been built perhaps not properly, and you hit it with certain streams of wind, then the bridge can act like a swing, and at some particular amplitude is going to resonate quite a bit, and so the amplitude is going to increase. Or same thing can happen with glasses, etc. These kinds of phenomena in general, so at some particular frequency or energy, what you're seeing is that the amplitude of the vibration is being increased. Okay, in particle physics, the same thing happens, but what gets increased is the amplitude associated with the probability that particles interact. Okay. So it's very much the same. It's analogous. It's just what you're increasing is the probability that some event will happen, right? At the end of the day, quantum mechanics, the underlying object, the underlying prediction is the probability for particles to interact, and so it's natural that that's the thing that gets amplified in some resonant phenomena. So how can this be explained? Well, let's go back to a little cartoon of particles that interact in some collision. Like I said, most of the times they just don't interact with each other, and so you won't see anything in your detector. They're just going to zip them by, right? But in some cases, if you hit them at some particular energy, they might be able to form an intermediate particle. Okay, so imagine that they're hit at the mass exactly at the energy where they can recombine into a particle. Okay, so basically they're accelerating and moving to each other at an energy that is equal to exactly to the mass of the particle in units of the speed of light being equal to 1, right? So E equals mc squared, where E is the energy of the incoming particles and m is equal to the mass of this little particle, this blue particle that we created. This is some particle with some resonance. It's a resonance with a mass m. It's just some particle that we've created. And after some time period, it will inevitably decay. Okay, it's going to decay again. If there was some probability for it to be created, there's going to be some probability for it to decay. And so eventually it's going to decay. And depending on how this particle behaves, it's in general going to decay in all possible directions. And so what you're seeing is that because there's some high probability of you producing this particle with that mass, it's going to start decaying and decaying and decaying. And so because of that, you're going to see many, many, many more events happening at that particular energy than before, because most of the times they just won't otherwise see each other. But because there's a high probability that you're going to create this particle, you're going to see more events. And that's what you're seeing. You're seeing an enhancement of the number of events taking place. And so that's how we see most particles in nature. We just see them as enhancements. They're just resonances, so their amplitudes are increased. They just increase the amplitude for the events to take place. And so that's how we see them in nature. Okay. And so, okay, so that's great. Hopefully that gives you a little bit of an idea on why, how and why we detect particles in experiments this way. Perhaps this is a good point to see if people have any questions before we start talking about a little bit of math. So if you have any questions, now is a good time to ask it. Okay, I don't see any questions, so perhaps let's just push on through. Okay, there's a question. We just got one.
Anonymous attendee says, does wave particle duality have any play in this?
Yeah, that's a great question. So it does, in the sense that let me see how. So I mean the thing that you're. So how do I reconcile wave particle duality in this context? I mean, the way that you can think about it is a great question, actually. So the way that you can think about it is you can certainly describe this as basically the probability of this event. Sorry, let me skip. The probability of that event, right? You had two particles, right? And then they overlap to create a new particle. So what you can do is you can construct the wave function. So I mean, I describe it just like I did, right? So there's like two particles that are off and they're not seeing each other, and then when they get pulled into each other, they get attracted to each other, right? And then the question is, they get attracted sufficiently that they'll form this intermediate state, right? So the question is, how do I then calculate the probability of this event happening? The way that you could do that is if you know the wave function of the out states where the two particles are free, right? And you just construct the wave function for those two particles. And you also know the wave function, which is inherently associated with the wave representation of the particles, right? So if you know the wave function for the intermediate, this little resonant state, then the probability is going to be proportional to the overlap of these two wave functions. And basically, it's going to be the overlap between your original wave function where the particles were free, and then the final wave function where you have the stable particle. So it's going to be actually the overlap of those two wave functions squared. Maybe that's a more technical answer than you were hoping for. Let me see if I can. Let me think a little deeply. Perhaps I can have a simpler answer. But that's a great question, actually. All right. Maybe Anonymous can tell me if they're satisfied or not. All right. Oh, there's one more question, or is that Anonymous getting back to me?
He's getting back to you. He said, it would be better if you could simplify.
That sounds good. All right, Anonymous. Let me think about it. How about that? Is that okay? Denver, I don't think the problem that I struggle with, and so a lot of times when we think about the wave nature of particles, we are thinking about the interference of different particles taking place, of like different particles propagating. But here we're essentially creating an intermediate particle, and it's hard. So the best way that I think about resonances, and this is perhaps my lack of understanding on how to think about the particle wave duality in this case, but the best way that I think about resonances, like the Higgs, is that you have particles that come in, and then they interact with each other. The force is attractive, but it's not sufficiently attractive they'll become a stable particle, and so they just become a resonant system, and so they're vibrating for a tiny little amount of time, and then they'll decay. And that's what you're seeing. How to describe this in terms of wave functions, in terms of waves, it's just not clear to me, actually. So I'm gonna have to think about this, but I appreciate it, Anonymous. I'll get back to you, okay? You guys are a sharp bunch. Is there any other questions, or is that still the same comment?
No, we just have anonymous saying now every time he asks or they ask a good question as anonymous, they regret not asking it themselves.
Oh, well, you can still say your name. Okay. So, all right, let me push ahead then, because yeah, that question really got to me. Nice job. All right, so the way that we can describe these probabilities of interactions, which is what we're going to focus on, because it's a nice exercise. It's going to give us a nice exercise to play with. Basically, it's a nice function that we can start to analyze. Is using a distribution that is called a Bright-Wigner distribution. It's after these two folks, and it's a distribution that describes the probability of an event. It's proportional to the probability, so it's not normalized to 1, but it's proportional to the probability as a function of E, which is the energy of the event, okay? And it carries this form, all right? And so we're gonna play with this quite a bit. So if it looks a little daunting at first, it's gonna become less daunting, hopefully, okay? And so E is the energy, right? So this is a function of E, right? And M is the mass of the particle, all right? And gamma is another variable, which is known as the decay width of the particle. That's nothing more than just, it's the inverse of the lifetime of the particle. So if the particle lives 1 second, then gamma is 1/1 second, okay? That's all. It's nothing too crazy. We call that the decay width because it's related to the width of the peak, okay? And so the gamma is telling us about the probability of the particle to then decay to 2 particles, all right? And so as a function of time, eventually this particle will decay. So if gamma is 0, then that would mean that the lifetime is infinite, right? And so that would mean that it will never decay, right? But most particles out there will eventually decay. There's only a few particles in nature that just never decay. I mean, there's nuclei basically, and not all nuclei. So the proton, for example, as far as we know, has an infinite lifetime. And so, but most other particles eventually decay. And so here, what we're going to start doing, and the reason why I like this is because it gives us some intuition, right? It's useful, but it's also a function that depends on 2 variables. And we're going to be, this is going to require some more challenge on our parts, okay? So here, what I've done is, here's a simple exercise, and you can actually respond to it right now. You don't have to like code anything up. Just try to get some intuition for this function. So here I've written some code for PBW as a function of energy, okay? And what I've done is that I just plotted this thing, PE, right, as a function of E, okay? And so the question that I want you to, so I did it for the same value of M, but different values of gamma, okay? So my question to you is, what value of M did I pick and why? Anybody? So the question is, so here I made some piece of code, right, where I calculated some term in the denominator and I call it temp1. I calculated some other element of the denominator, call it temp2, and then I divided temp3, which is a numerator, by the sum of temp1 plus temp2. And so from this figure, from the figure here, and looking at this distribution and understanding and looking at the equation, right, what value did I pick for M? I see somebody ask, suggesting that I use the mass of the proton. No. I'm looking for a number like 1, 2, 3, 5, could be 3.5, it could be 3.1. I'll give you a hint. It's a number between, anonymous says 2.5. Why anonymous? No, but like now there's so many anonymous, it's impossible to know. Everybody's anonymous. Anonymous, why did you pick 2.5? Which is right. Anybody? So, all right, I'll rescue Anonymous. I think Anonymous knows the answer, but maybe it's a little shy.
I was looking at where the peak was.
Oh, very good. Yeah, it's the peak of the graph. Yeah, very good. So if you see, the question is, when is this the biggest, right? Right, the biggest value, right? The thing in the numerator, it's just a number. This is not going to change, right? It's just going to be some number. And so when is this going to be biggest, right? Well, it's going to be biggest when the denominator is smaller, right? But this won't change as a function of energy, right? There's just some number again. And so the denominator is going to be smallest when this is smallest right here. And this is a positive number, and I'm always adding it, right? So this is going to be smallest when this is smallest, right? This whole thing is a positive number. And so this is smaller when E is equal to M. And so when E is equal to M, this is going to be biggest. And we see that the peak for all of them, so the biggest value is always when E is equal to 2.5. And so E being equal, or M being equal to 2.5 is absolutely right. Does that make sense to everybody? Is anybody confused? Because we can flesh it out some more. Is anybody requesting for more clarification, or is everybody on board with a hand wavy argument?
Anonymous asks, could you talk about it in a bit more detail?
Sure, yeah. Give me a second. How about I'll just pull up my iPad. Give me a second. Just connecting my iPad. It's always better to just write something out than like me wave my hands. All right. So let's look at the equation. So I have PE is equal to M3 gamma. No, just gamma, right? And then I have E squared minus M squared all squared plus M squared gamma squared. Right? And so the question is when is PE biggest? Right? And so we know that this thing as a function of E, when we fix M and gamma, meaning I'm not varying M and gamma, right? But I am varying E. Okay, so the question is, for what value of E will this P be biggest? Okay, this is a general problem in calculus, and I mean in math in general, when we're interested in finding minima or maxima or functions. Okay, this is a simple one because the numerator doesn't vary with E, okay? And so finding the maximum of PE is equal to finding the minimum of the denominator of PE. Okay, and so we just translated the problem to, instead of finding the maximum of this, right, we're gonna find minimum of E squared minus M squared plus M gamma, right? All right, everybody with me so far? So that's our goal now. So we want to find this, right? And then the point is that this is just a positive number. So this is a positive number. This is a number that is greater than 0. Well, it's greater than or equal to 0, okay? This one is always greater than 0. All right. And so when is this at minimum? Well, the minimum, because this is just some number, right? I'm always adding some positive number, right? This doesn't do anything. So the minimum is when this is minimized. It's when this thing it's minimum. And this is going to be a minimum when it's equal to 0. And so the minimum is when E squared minus M squared all squared is equal to 0. And so I can take the square root of both sides. And so the minimum is equal to, corresponds to this, which means that the minimum is when E is equal to M squared. And so we see that the minimum of the denominator, which is the maximum of this thing, coincides with 2.5. And so that tells me that the mass that I used was 2.5. Does that clarify things?
No additional questions, but Anonymous made a good point before you started with that. They want you to label your axes on your graph.
Oh my God, Anonymous, so picky. I like it. E. I'll put that right here. And that P of E. Do I get a passing grade now, Anonymous? All right. Okay. Hopefully I get a passing grade. All right. So now, the things that, you want to try to do, right, in any distribution, right, any function that you see, doesn't have to be this one particular, right, but like think about what happens to the peak, to the distribution as you vary the variables, right? We see that if I shift M, if I make M bigger, this is going to go this way, right? The next question is what's going to happen to the distribution if I decrease gamma or make it bigger, right? If I make gamma smaller, what's going to happen is that distribution is going to get more narrow and taller around the peak, and it's going to be smaller everywhere else. And so this is a fun distribution to play with. Okay. All right. So I've motivated now these kinds of distributions, right? They naturally they behave this, they have this nice little bumpy behavior that we're looking for, right? They have some physical, we've developed some physical intuition, right? That the peak is going to give me the mass of the particle. The gamma is going to be related to the lifetime of the particle. And so then the question is, given some data, right? You have some data. How do you know which values are best describe the data given this distribution? In other words, which values of M and gamma should I use? And so the question is, how do we do this? How do we optimize these parameters? And the answer is through fitting. Hey. So that's what we're going to talk about next. How do we fit anything? How do we fit some function into some data so it matches the data as best as possible, right? And this is how these lines were made, is by doing fits. And so here's my little intro to fitting. So one way that you can do this of trying to find the parameters, right, is that you have some data, and here's some data I've generated, right? And you can see that the data, it's peaked around 3, right? It has some sort of width. And in fact, I generated this data using some M and gamma corresponding to 3 and 0.5. I just picked some specific discrete energies. And I just, you have some values at which I'm taking data. This could be the energy that I tuned the initial particles to be moving at, right? And so, yep, there's my data, right? And here I'm doing guesses of what the distribution would look like if M and gamma were, say, 2 and 0.3. Also anonymous, I'm sorry about this, but the axes are the same. I'm picking the x-axis is energy, and the y-axis is PE. Anonymous is making me second guess my plots now. And so this is what I get for some value of M and gamma. And then the blue, I get another value of M and gamma, and then the red one. And you see that I start dialing M from 2 to 2.5 to 2.8. It starts to look closer and closer, right? And so it looks like I'm getting closer and closer, but maybe not quite getting there. I vary gamma from 0.3 to 0.4 to 0.45, etc. Right? I'm getting closer and closer. And so what I want to do is define a measure that effectively counts the distance from the distribution that I have, and then the data. And then what I want to do then is minimize that distance as much as possible. Ideally, I want to set that distance to 0. And so this is what brings me to effectively what is known as what effectively is a distance. So this is what is known as an example of a goodness of fit. This is the simplest goodness of fit, which is a lot of times called the chi-squared. So the chi-squared is just it's a simple measure that tells you how good your data is described by some ansatz of a function, okay? So I have some function that depends on some parameters, and I want to tune those parameters to describe the data. And so here is my first example of a chi-squared, okay? I'm going to write the chi-squared several different ways, several different ways for different examples. So here's the simplest one, okay? Imagine that I had that data from before, all right? And what I have now is the y's are the average of the average number of events, right? So the things on the tops at some, so the average bin, so let's say average number of events for the ith energy. Let's move this around. Boop, boop, boop. Okay. So it's just some number of events. There's some data that I've collected, and I called it Y, and I'm summing over the different binnings, really. So that in this case, this would be like energy 1, energy 2, energy 3, energy 4, blah blah blah, all the way to the final energy, right? And the Y is just a value here. So this would be like somewhere around 0.5. This one would be around 1. This one would be close to 2, et cetera, et cetera. Okay. And so that's what the Y bars are, okay? The sigma i's are just the standard deviations, which I have them here. There's some standard deviation. I can't remember what I picked. It must have been, something around 0.1, I think is what I picked. So you can see there's some standard deviation, there's some error associated with that data, right? And so the chi-squared is defined as the distance between them squared. You see I have a squared. So there's a distance between my my data and my prediction for the data, given some value of m and gamma evaluated at that particular energy. And I'm dividing that by the standard deviation. I'm allowing there to be some deviation between the data and my prediction that is measured by the standard deviation. And so now what I can do is, for my guesses, right, evaluate the chi-squared for the, let me hold up to the anonymous standard of plotting. I'm gonna have PE and E. Let's put it over here. Put it there. Good. Don't have it here. I do now. So now I'm just showing the same plot, but this time now showing the chi-squared. So I just evaluated the chi-squared. The distance between, so in this point, for example, the red, right? The PI for this energy is way up here, right? So I would be evaluating the distance between this red point and this little black point divided by the uncertainty. And then I would add the distance between this black point and this red line over here divided by the uncertainty. And then I would evaluate the distance between this black point and this red point divided by the uncertainty. And I would add up all those all the way from this to this, from this to this, and I would get a chi-squared of 2,500. So it's crazy big, really big. Now I then do that for the blue line, right? I do the distance between these guys, distance between these guys divided by uncertainty, and so forth, and I get something a little bit better. 2,000, still awful, right? It's a huge distance. And I do it for the green, right? And you're seeing, look, this goodness of fit, right, is going from 2,600 to 2,000 to 500. It's getting better and better, right? And at least this is allowing us to figure out how bad we were guessing, right? We were doing an awful guess, but now we know that this is indeed telling us that the red is a terrible, terrible guess. The blue is a terrible guess. The green is, it's a bad guess. And so we get closer and closer to the right answer. So I see a question. How do you get the standard deviation of the data? Well, in this case, it depends on the data. Here, I just generated a standard deviation, so I'm giving it to you. But the way that you can guess the way that you can measure the data, the uncertainty in general, right? It's just you have some distribution for a number of events, and it depends on. So calculating the experimental uncertainty is maybe I won't touch on that. I can tell you that for some quantities, the way that you would do it is just, you would calculate the same thing, perhaps statistically, and you just do it over and over again, and you get some mean value, and then from that distribution, you should be able to calculate the uncertainty on the mean value. So that's essentially how you could do it in general. So for this given event, you have it as some energy, and you just do it over and over again, and you get some distribution for that mean value. That's essentially the idea, without going to technicalities. Okay. And so hopefully that answers the question, at least to some satisfaction. And I mean, calculating uncertainties in general is a challenge, and depends on the specifics of the thing that you're trying to do, right? And so now what we've done is now translated what the chi-square allows it to do in general, right? Is that it translates now the problem of trying to match to the data to one where we're trying to minimize this distance, right? We're trying to minimize this thing right here. And so we're translating everything into a minimization problem. And so you can think of the chi-square is now a function of m and gamma, and the optimal values of m and gamma are the ones for which the chi-square is at its minimum. And so here, it's a two-dimensional function, right? It depends on two variables, and we could do contour plots if we wish, but I chose against it because I find that sometimes contour plots are hard to read. We know that the data was generated using m of 3 and gamma of 0.5. And so what I did here is that I first picked gamma of 0.2, and then I plotted what the chi-squared was for all these values of m. And you see that I get, wild numbers in the order of 4,000, even bigger, right? They get smaller and smaller as they get closer to m of 3, right? And then if I dial gamma to 3.5 to 0.3, I get this curve over here, right? Again, it gets minimized in this region. And then if I picked 0.4, I get something that gets minimized even further. And eventually, if I pick 0.5, you see that this goes all the way to 0. And so I find its true minimum, which is over here. And so what we basically can translate this to is what we want is to find a minimization. When we want to minimize this function, I won't talk about how you can, in general, find these minimas. This is always a challenging task. There's many routines out there for finding the minimums of multivariable functions. The simplest way you can imagine, right, is that I just do a scatter plot in the two-dimensional plane of m and gamma, and just try to find the minimum that way, just picking random numbers and just brute force all the way there. Fortunately, there's many optimization routines out there, and here's a link of a place where you can play around with different minimization routines and visualize them. And instead of me touching on them, I'll just put on the chat. You can also see them from the slides. And so here, instead of discussing a lot of how you can do this, we're just going to use existing routines in Python to help you minimize, okay? And so for this, we're going to use a library called SciPy, which has different routines in there. So Sci is for science. And so there's a lot of optimization and root finding routines. And so here's an example of me using that routine in my code, where I define a chi-squared function. And let me walk you through this. So the chi-squared function, I made it depend on two variables, which are in a list format. So it's m underscore gamma. I then translate this into a scalar, into two numbers, m and gamma. I then call my p underscore bw function, which I define elsewhere, which gives me back the probability distribution according to a Breitwigner. And then I feed some list of numbers, which are the independent variables which appear on the x-axis, okay? They're discrete, they're global variables, and this gives me the PIs. I then also have global variables, so the y's, which are the dependent variables, the black points, right? And then here is a place where I could have done a for loop, right? To evaluate the sum over the chi-squared. Let me remind you what the sum looks like. Let's pull it up. So that's an example where the chi-squared is equal to the sum of the probability distribution being evaluated at some mass and gamma and some energy minus the data evaluated at that energy, all squared, divided by the standard deviation squared, right? So I could have made a for loop, right? But this is going to be really, it's not, I mean, there's not so many points, so it's not that big of a deal. But instead, I do something that is always going to be faster, which is I call the PI, I made this into an array. The Y's are these guys, and they're an array. The SIGs are also arrays. And so then I just grab this thing, take it to a second, I just raise it to a second power. I could use the numpy function for squaring. And then I take the sum, and that's it, using the numpy function for sum, and I return chi2 squared, the chi-squared, okay? I also defined the number of degrees of freedom, but we don't use it here actually. So this is not doing anything. You could just scratch that. In fact, let's just scratch it. It's not doing anything in that code. Okay. So this thing, this code just returns a number. And so then my minimization routine is calling this function over here, okay? And it's using the built-in function minimize, which exists within optimize, which exists within SciPy, okay? So I put in the documentation for it, and I called it with, so I call this, which takes in the function that you want it, and then the variable that you're minimizing. This variable could be one-dimensional, two-dimensional. I mean, it could be one variable or multi-variables. It's using the this particular routine method, which is described there. It's also explained in this little video that this interactive page that I sent you. But it's just some minimization routine. And what else? So that's it. So you have to put in some guess in general to tell it where to start looking. So here I've made some guess just from looking at the data. I said, oh, start around 2 and use gamma of 1, just a random guess. And then the routine gets me back this value right here, this m gamma underscore gamma. And if you print out m underscore gamma dot x, it gives you back the final values, which is this thing right here. And you see that what it gives me is 3.999 blah 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 point, and that for the first variable, which is my m, and then for the gamma, it gives me back 0.4999 blah blah blah. So it's essentially just 3 and 0.5, right? And look, indeed, my peak is at 3, and the width, which is the distance between, it's basically half the length of this object, is 0.5. So that works really well. It's very fast. And so you're going to play with this. So maybe this is a place to see if people have any questions. Before I describe the exercises that you're going to do. But this is the idea. You're just going to play with this built-in function for minimization. You're going to write your own chi-square fitter using existing routines. And this actually is close to being just very useful for many, many different data analysis. I've been a little glossy on the details, the formal math behind it. There's some subtleties that one needs to take into account for doing slightly more complicated data analysis, but this is like the bread and butter, and it turns out to be very useful in many things. So Are there no questions at this point? Because I can just keep on going. Just checking my time. Okay, if I don't see any questions, maybe I'll just keep on pushing. All right, so here's your first exercise. Or my second exercise. I guess I gave you an exercise, but I was trying to get you to write your own code. Okay, all right, second exercise. Let's fit a constant. How about that? Let's just make it easier, right? Let's do a super warm-up exercise. So I generated some data. Okay. And it's already in this folder for you. So go to that folder right now or later. And what you'll see is data that looks like this. There's going to be some independent variable column. There's going to be the average dependent variable, and there's going to be some standard deviation. I just generated it, okay? It's just some numbers. And what you need to do is load up the data, right? Using whatever functions you want. I gave you some simple examples of how to loading functions. And then this load text makes this into an array. If you then take the transpose of that array and just spit it out into X, Y, and SIGs, that's going to give you back the independent variables, the dependent variables, and standard deviations of the variables, okay, in an array format. And then at that point, you can do, you can then put that through your chi-squared, do the same types of tricks of like subtractions, raising things arrays to powers, summing using the sum functions that are numpy, all those things you can do with arrays. So it's very powerful. All right, so load that data, and then the thing that you have to do is fit that data to a constant. Here you can, first plot the data, right? So you see what you're looking at, right? What you can see is just basically some number that is oscillating around 1,000. Okay, so it's very easy. And so, it's not, I shouldn't say like super easy, but like it's the easiest example I can think of, let's say it that way. And so you have your data yi, you subtract, so the chi-squared for this would be the data minus the constant, right? The number that you're trying to find divided by the standard deviation, all squared, sum over all elements, okay? And so what you're trying to find is the minimum of this. And the minimum that I get corresponds to a value of C that is equal to approximately 1,000. All right, so try to reproduce this plot. How about that? Good. Are there any questions about this exercise? Because that's the first. So if there's any questions about this, I'm sure you're going to have questions about other ones. So don't be shy. Ask the questions now before we go into something more complicated. Going once, going twice. Sold. All right, let's keep on going. All right, let's make it more fun. How about that? Okay, that was too easy, perhaps. So next, let's fit a straight line. Okay, we already fit a constant. Now let's fit a straight line. How about that? Instead of fitting just any random straight line that I create, I figured we would do something more fun. I'm giving you real data that has been obtained from real calculations out there, from real scientists doing real simulations of nuclear physics. And so what I'm giving you is calculations that were performed using simulations of quantum chromodynamics. These are referred to as lattice QCD meaning quantum chromodynamics. And what is done is that the dynamics of quarks and gluons are put into supercomputers, and the only variable that is being used, the only variable that is needed to be tuned or introduced in the simulations is the value of the quark masses. In fact, this is a remarkably fascinating and amazing thing that is true in particle physics, that there's only a finite number of parameters, which in principle describe all the quantum mechanical phenomena, all the subatomic physics, all the atomic physics and molecular physics that we see, science, I mean, in general, biology, everything, right? Like can all be described by a finite number of parameters, right? And so in these simulations, what we're seeing is that by essentially tuning one parameter, we're able to start seeing both the, the mass of the lightest particles, namely the pion, the nucleon, and many others, as well as their properties and how they interact with each other. So it's that's the beauty and power of these kinds of things, okay? And so what I'm gonna give you are the things that have come out actually from these simulations from different groups around the world. On the first column, I'm giving you the masses of the pions that they've obtained when they vary the quark masses, okay? So there's some weird numbers, okay? They're all a little bit different, but because they're using different values of the quark mass. And what comes out on the second one is the nucleon mass, okay? On the last column is the standard deviation, okay? Standard error for the masses. So yeah, I gave you that data. It's in this folder, so go load it up. And it's real honest to God data. And so here it is. And so let's look at it. And the thing that you can see, right? So let's look at it. And I did label this one properly. Thank you, Anonymous. So on the y-axis is the nucleon mass in some units, okay? Forget about the units. It's just a nucleon mass. So meaning the proton mass. And the x-axis, where you're seeing is the mass of the pions, the lightest degree of freedom of the theory. And it turns out that this mass is proportional to the square root of the quark masses. How that happens, I mean, it's amazing, but it's outside of the scope of this class. But basically, the pion mass is proportional to the square root of the quark masses. And so what does this mean? It means that if I take the quark masses to 0, and so here's a 0 of m pi. So if I take the quark masses to 0, I'm also taking the pion mass to 0, right? So they both coincide in this limit, in the limit that they're both 0. And so what you're seeing is that as I dial the quark masses, right, to be heavier and heavier, the nucleon gets heavier and heavier. And this makes sense, right? Like the proton is just essentially it's like a bag which has quarks in it, right? And so as you make the quarks heavier and heavier, the proton itself gets heavier and heavier, right? That's fine. The thing that's weird is what happens in this limit, where we take the quark masses to 0, then the pion is massless, but it turns out that it looks like the nucleon is not massless, right? And in this limit, the Higgs itself doesn't matter because the Higgs is a source of the masses of the quarks. And so if we've removed the masses of the quarks, the Higgs is just doing nothing to the quarks and is doing nothing to our masses, right? And so in this limit, the Higgs plays no role in generating our masses, right? And we're seeing that this number turns out to be really far from 0. And so the question is, what is the number in this limit where the quark mass is exactly equals 0 and therefore the Higgs doesn't matter? What number would we get in this weird universe, right? And in other words, how much does our mass get generated and come from the Higgs, okay? And so how can we assess this? Well, all we really have to do, right? It's a lot of philosophical questions, a lot of hypothetical questions, but in practice, all we have to do is just grab this data, all these little points, right? Which look to be well described by a straight line, and just fit it to a straight line. Just honest to God, just fit it to a straight line. And so here's the function that you would evaluate, where you fit into a straight line of A plus B times the pion mass, okay? So that's it. That's all you have to do. And then once you do that, we'll talk about your results. And then the last exercise, I think this is the last one. Let me see. Yeah, very much the last one. And then we'll call it a day. How about that? The last exercise is, now I've generated some Breit-Wigner distribution, right? We've talked about the Breit-Wigner quite a bit, right? Here's some fake data. And I put the data on this folder right here. And the question is, what's the value of M and gamma that I picked? Okay. So all you have to do is just write a chi-squared for this, right? And minimize it for M and gamma. There's my result. Sounds good. All right. So I think that's a perfect place for us to stop for the day. Let me just recap the things that we covered. So we introduced one really powerful concept, which is the goodness of fit, which is basically giving us a distance between some function that we want to impose on some data, and it's giving us a measure for the distance between our functions and our data, and it allows us to then have a well-defined algorithm for us to be able to find the best parameters that describe our existing data. This is just powerful everywhere in any sort of data analysis. To play around with some data, we've motivated the use of Breit-Wigner distributions in particle physics and in resonant phenomena of all kinds, and well, I mean, just particle physics really in this case. And this is a 2-parameter distribution which depends on M and gamma, nothing else. And so these parameters have some physical meaning. They're associated with the mass of the particles, of the intermediate particle, as well as the lifetime of the intermediate particle. And so this is very useful in experiments. This has led to many discoveries, including the Higgs. And so hopefully after this, you will have a better understanding of how to use these. And certainly the chi-squared goodness of fit is going to be useful in all sorts of scientific fields, not just physics. So I think that's it. I'll wait to see if you have any questions. If not, I can tell you that next time we're going to start working on we're going to start playing a little bit with calculus, and we're going to start eventually, hopefully by next week, we'll start playing with infectious disease models, which is going to be quite fun. And I think Connor is going to have some data analysis project for you to consider sometime next week. Is that right, Connor?
Yeah, at least the marble guessing one. Hopefully the climate model, if I can find dense enough measurements.
Sounds good. Okay, cool. Are there any questions at this point? Does everybody know what they have to do roughly? I'm going to assume that no probably means no questions. It would be good if I can give a recap. Very good. Sure. So let me just recap. So first, maybe let's go all the way to the beginning. So if you're still catching up, don't worry. The projects that you need to do from last week is calculate pi using random numbers. Okay, so that's the first thing that you need to do. Are there any questions? How about this? If there's any questions about each one of the projects, just ask them. Okay, so the first one is to calculate pi using random numbers. Okay, are there any questions about that project? I'm gonna assume that's a no, but you can stop me. That the second project was, I gave you some data for a parameter P, which is the momentum of some outgoing particle after a decay of a single particle. And I asked you to find the mass MC. And what you should be seeing is that I gave you some list of momenta, right? You should have some distribution momenta of this form. And then you just have to propagate that through this equation to find the distribution for the mass MC. And so that's a goal. So I'll leave you to do that. So that's from last week. Now let's move on to the exercises from this week. Okay, this is my exercise number 1. So exercise number 1, let me just copy it over here with the other exercises. So they're all in one little bundle. So exercise number 1. Exercise number 1 is write code for the Brett-Wigner distribution and just make these plots, just reproduce these plots, okay? Make sure that everything is working. So you have m equals 2.5 and then gamma is 1, 2, 3. And get some intuition for what happens to the distribution as you vary gamma, okay?
Anonymous has a question about the momentum exercise.
Oh, yeah.
Yeah, they're wondering if the masses A and B are in the Dropbox.
I gave them to you. They're not in the Dropbox, but they're in the I think it's 2 and 1 respectively. They're right here. Yeah. You see, so they're on the slides. MA is equal to 2 and MB is equal to 1.
And the slides are in the Dropbox, correct?
That's right. Yeah,
Okay.
all the slides are on the Dropbox. Everything is on the Dropbox. So, yeah. So maybe I should have said yes. They're in the Dropbox. They're just inside of the slides. Okay. So, okay. So first exercise for today is this plot. Just generate this plot yourself, right? Varying gamma and fixing m to be 2.5. Okay. Second thing is to fit a constant. Okay. And so I gave you some data for a constant, which basically has some independent variable that is just numbering the measurement. It's not doing anything really. The dependent variable they're trying to fit is these numbers over here. Okay, and they have a standard deviation of this form. And so if you load it up using some code like this, which you can write yourself, you'll have an array for the x's, the y's, and the sigmas. And then what you need to do is write a chi-squared for this, which is only going to depend on c, which is the variable that you're trying to find. And so you're trying to find the minimum of this as a function of, sorry, my Siri started talking. So you're trying to find the minimum of this as a function of c. And you're going to use the same optimization minimizer that we used in here. So this is a existing Python optimizer that we're going to be using, the optimize underscore or dot minimize. So you're going to write something like this, but for instead of a 2-parameter case, a 1-parameter case. Okay. All right. That might be a little challenging, but that's okay. I mean, just think about it. What you have to do to change this code to allow for just one variable, which basically means you're going to have one for a constant, which instead of having a list like this, you're just going to have a single element. And remember, I don't know if I made this clear, but it's a good time for me to re-emphasize this. This is what let's look at, yeah, here. So here is project on #4, okay? The slides are there, right? Your data is here, right? This is the data that I'm giving you. Here's my code. So if you ever get confused and you want to just look at some code to, if you get so tired that you can't find the solution yourself, just look at my code. I've been giving you all my codes are available. So you can see in project 3, if you're stuck on the decay thing or the calculation of pi, right? Here's calc_pi. And here's the figures that I get. So you have all of my code. So don't get overwhelmed, don't get discouraged. The idea is to make this as fun and as accessible as possible. Okay. Just try to understand what the code is doing, of course. Yeah. All right. So that's a calculation of the constant, right? Next is fitting this data to a straight line. Okay. I told you this whole spiel about quark masses and Higgs and blah, blah, blah. But all you're really doing is just fitting to a straight line. I was just giving you a motivation to fit a straight line. Okay. And so here's the data is the black points. They're in this folder over here. And then you're going to grab the data and fit it to a straight line using 2 parameters, A and B. And you're going to find the values of A and B that minimize the chi-squared. Okay. And you should see a line like this after you plot it. Okay. And so hopefully that is clear. I see that. Yeah, so there's a question about the low text function. They have to be, you either have to give the full direction, the full address of where the file is at, or you can just put it, just make sure that it's on the same folder as your code. The easiest is to put them on the same folder as your code. I see Anonymous is saying, I know that beggars can't be choosers, but it would be really helpful if you could add in a bit more comments in your code. Very good. I can work on that for sure. I thought I had put quite a bit of comments, but I probably got lazy at some point. So I'll step it up. I'm sorry, Anonymous. Anything else? Okay. So then the functions that we're doing, right? This is so let's go back to the constant. This is a single variable fit, right? We're just fitting 1 parameter. And here we're fitting 2 parameters, right? It's a straight line, but which can be described by an offset and the slope, right? That's all you're trying to calculate. And the Brightweighter is again is a 2 parameter fit. It's just a little more funky, right? It's just more fun looking, right? It doesn't look as boring as a straight line, but it's essentially, I mean, it's just a 2 parameter fit, right? It's just finding the peak and the width of the peak. All right. So I gave you some data here and you can load it, right? The same way that we've loaded all the other stuff. And then you write a chi-squared just the way that I did before. In fact, you have essentially a picture of me. This is essentially my code for minimizing the chi-squared of a Brightweighter. You're gonna have to write a chi-squared for the constant, for the slope, for the linear case, and then for the Brightweighter. You're gonna need 3 different chi-squares, and you're gonna need 3 different minimization routines. You can make things that are more complicated, but that's the simplest way to do it. Just write 1 for each case. Okay. All right. How is that for a recap? Anonymous number X. Unknown anonymous. Are you happy with that recap? Is that clearer? Or were you looking for another kind of recap?
They said, yes, very happy.
Oh, okay. Good, cool. All right. So Am I free to go for now? Can we call it a day? We'll pick up on next time. We'll start talking about calculus related stuff. If you've never seen calculus, that's okay. That's the point. It's directed at you, at the people that haven't seen calculus before. If you've seen calculus, some of it will be a review, but it's okay to see it again. And then we'll touch on things that are new eventually. Are we good?
It seems as though we are.
Sounds good. Okay, cool. All right, then let's call it a day. We'll get back here Friday. Please, please, please ask your friends and family to guess about the marbles. It will make Connor very happy. And we know that we're all here to make Connor happy. So don't disappoint Connor. Okay. All right. I hope everybody's doing well in your corner of the world. And we'll see you again Friday. Okay. All right. Take care, everybody.